Hello, my dear friend. My name is Dr. Amit Tomar. I am Senior Assistant Professor in Department of Physics and Astronomical Sciences, Central University of Jammu campus. Today I am here to present a very important video lecture regarding your CUET entrance examination in physics. So, आज का जो टॉपिक मैंने डिसाइड किया है आपके एग्जाम के लिए, वो मैंने लिया है यूनिट 9 से इलेक्ट्रॉनिक्स डिवाइसेस, और इसको लेने की एक खास वजह भी है मेरे पास कि एनटीए ने कुछ सिलेबस आपका रिवाइज किया है, और रिवाइज सिलेबस में यूनिट 9 के अंदर, जिसका नाम इलेक्ट्रॉनिक्स डिवाइसेस है, कुछ नए टॉपिक्स ऐड किए हैं, जैसे कि एक्सट्रिंसिक सेमीकंडक्टर्स क्या होते हैं, इंट्रिंसिक सेमीकंडक्टर्स क्या होते हैं, और उसके बाद पी टाइप, एन टाइप, और उसकी जो एप्लीकेशन है वो पीएन जंक्शन डायोड के रूप में इन टॉपिक्स को शामिल किया गया है। सो मैंने सोचा कि जब कोई टॉपिक्स किसी एग्जाम के सिलेबस में फर्स्ट टाइम नए ऐड किए जाते हैं, तो उन पे आप मान के चलिए आपको निश्चित रूप से क्वेश्चन वहां पे मिलेंगे। तो यही एकमात्र कारण है कि मैंने आज इस टॉपिक को आपके लिए लिया है, और मैं कोशिश करूंगा कि इस टॉपिक को पूरा कवर करके और इसको इस तरह से बाइंड अप करें कि आपके सारे सवाल जो हैं वो इसमें कवर हो जाएं। सो हम अब इस लेक्चर को शुरू करते हैं, और पहले आपको एक्सट्रिंसिक सेमीकंडक्टर क्या होते हैं, इंट्रिंसिक सेमीकंडक्टर्स क्या होते हैं, और कैसे फिर इसको हम जो हमारे एक्सट्रिंसिक सेमीकंडक्टर हैं उसे पी टाइप में और एन टाइप में कन्वर्ट करते हैं, और फिर उसकी एक एप्लीकेशन जो है उसको हम डिस्कस करेंगे, जिसको हम पीएन जंक्शन डायोड बोलते हैं। तो आप लेक्चर को ध्यान से सुनिएगा और पूरा लेक्चर सुनिए पेशेंस के साथ, तभी आपको पूरा आउटपुट मिलेगा। स्किप करने से या जल्दी जल्दी सुनने से उसका पूरा जो सिग्निफिकेंस है लेक्चर का वो खत्म हो जाता है। तो पेशेंस के साथ आपको लेक्चर सुनना है, तो एंड में फिर आपको काफी अच्छा महसूस होगा। तो मैं अपना लेक्चर शुरू करता हूँ। लेट स्टार्ट।
So here is the first PPT. In first PPT, I have a heading with a question mark. What is a semiconductors? So first we have discussed some basic theory and some basic physics regarding semiconductor working, semiconductor manufacturing, and how they react when we put the semiconductor in the external electric field. So today we are going to read the physics behind the semiconductor structure, semiconductor working. So let's start. As we all know, we frequently listen three words in our daily life regarding the electronic applications like metal, non-metal, conductor, semiconductor, insulator. So among these all words, semiconductor has some special potential because of its special structural property, and we are going to discuss this property in a very detailed manner. So semiconductor is a material whose conductivity, the word conductivity here regarding the electrical conductivity. So electrical conductivity of the semiconductor lies between the conductor and insulators, or between or in between them. Basically, this sentence has a very broad meaning. It is not just as simple as you listen or as you see here. Semiconductor is a material whose conductivity, electrical conductivity, lies between the conductor and insulator or in between them. This sentence means that semiconductor has the property of the insulator. Semiconductor has the property of the conductor also. So it is very important regarding the current generation or the next generation electronic devices. As per our need, as per our desire, as per our requirement, we have to make changes in the semiconductor manufacturing process, and we get the desired material. If we want to need a high conductivity material regarding our basically electronics device formation, so we have to use a high conductivity semiconductor. If we require a low conductivity material regarding somewhere we require a special kind of electronic devices, so we have an option during manufacturing the semiconductor material for that particular device. Then we have to make a low conductivity material. So this is the beauty of the semiconductor. During the manufacturing process, we have power to tune. We are in the position we may tune the conductivity, electrical conductivity of the semiconductor as per our need, as per our requirement in daily life electronic device application. no other material available in the nature which has the same property. Like in case of metal, we don't have such power. We don't change the conductivity of the metal as per our requirement. They have the fixed electrical conductivity like copper, aluminum, gold, silver. They have a very high conductivity. And if we want to make some devices in which we have to create a low conductivity material, then these material are not useful for that particular purpose. So this is the beauty of the semiconductor. We may twin, we may construct, we may change the electrical conductivity of semiconductor as per our requirement. In other words, the electrical conductivity of the semiconductor material are flexible. It has a very wide range. We have a very high electrical conductivity semiconductor. We have an intermediate electrical conductivity semiconductor, means the conductivity varies high to a low values. So as per our requirement, as per our desire, we may tune the semiconductor electrical conductivity during the manufacturing process. How we change the electrical conductivity of the semiconductor, how we manage, how we tune. Tune means just we make as our desire, as our requirement. So we may manipulate the electrical conductivity of semiconductor because of its special structural property, and this process is known as doping. So here you have seen the PPT. There is some common example of semiconductor like silicon, germanium, gallium, arsenic are the compound semiconductor. These are the two elements in the semiconductor. But more commonly, your concern here is a silicon and germanium, where we have to start. So semiconductor, as you see in this figure, the block diagram shows the semiconductor have the two branches. The one is the extrinsic, the another one is the intrinsic. The extrinsic semiconductor is another two type, P type semiconductor or N type semiconductor. Here N stands for negative and P stands for positive. We will discuss in a very detailed manner in next PPTs. So for this PPT, I think now it's time to move further. Semiconductor is basically two branches, extrinsic or intrinsic semiconductor. Basically, intrinsic semiconductor is a pure form of semiconductor. The semiconductor material like silicon and germanium, they are in the pure form, and in pure form, they don't have any impurity or any other element in their structure. So this is called the intrinsic. Intrinsic means the pure form. And when we, during manufacturing, we are adding some material from some elements from outside or to make them as extrinsic semiconductor, and because of addition of these additional element from outside, the electrical conductivity of the semiconductor increase drastically. So doping is the process by which we are adding a outside element in the pure semiconductor so that their electrical conductivity may increase to a very high limit. So now it's time to move further. So it is a brief overview regarding the types of the semiconductor. As you see in the figure, we have two pictures regarding intrinsic semiconductor and extrinsic semiconductor. So as you see in a intrinsic semiconductor, we have a uh, simple atom which has a four valence electron in the outermost orbit, and these four valence electron is shared by the another atom, nearby atom, and so that they complete their outermost structure, which is complete by the eight electron. So this is a basically structure of the intrinsic semiconductor. So let's read these points one by one, and then we explain individually. So first of all, we have a definition regarding what are the semiconductor. So these are the material with electrical property between conductor like copper and insulator like glass. Conductivity of the semiconductor depend on the temperature and the impurity. Basically, impurities are the element which we have to add from outside during manufacturing the semiconductor so that to make them extrinsic semiconductor, and the benefit of adding impurity is that these impurity increase the conductivity of the semiconductor drastically to a very high range, or by adding the quantity. So by adding impurity, we may increase the electrical conductivity. So what are these impurity? We will discuss in the next PPTs. Common example of semiconductors are silicon and germanium. So basically, semiconductor are of two types: intrinsic semiconductor and extrinsic semiconductor. Intrinsic semiconductor are pure form of the semiconductor with no impurities, and basically conductivities of pure semiconductor is like of insulators, and extrinsic semiconductor are the semiconductor which we have manufactured in laboratory in industry. These are the semiconductor which is doped, or the word used, which is substitute by some outside element, and then the material comes out in the form of the extrinsic semiconductor, which is very useful for electronic device application. So extrinsic semiconductor are of two types. The one is the N type and the second one is the P type. So here we have to explain N type and P type. So N type is the extrinsic semiconductor in which electron are the majority charge carrier, or in other words, electron are responsible to conduct the electrical current inside the semiconductor. In p-type semiconductor, we have the majority charge carrier are holes, which are positive charge carrier, and in p-type semiconductor, these positive charge carrier holes are responsible to conduct the current. So I want to just elaborate this point in some easy language. Basically, in N-type semiconductor, the electron are responsible to move here and there to conduct the current. In p-type semiconductor, the holes are responsible to move here and there to conduct the current. In p-type, electrons are not in the position to move here and there, and in n-type, holes are not in the position. So in n-type, basically n-type is electrically neutral. If we don't give the electric field from outside, then the n-type and p-type both are electrically neutral. They have equal number of positive and negative charge. Keep that in mind. N-type means here is the electron which are responsible to conduct the current. Here is the electron which are moving here and there. In p-type, here is the hole which are responsible to conduct the current. Here is the hole which are moving here and there. So they both have equal number of positive and negative charge. They both have electrically neutral. But the cause of current in n-type is electron, and the cause of current in p-type is hole. That's why their nomenclature is n-type and p-type. Keep that in mind. It is as simple as I told you. So in this PPT, we have a two figure, like intrinsic semiconductor we have discussed, and extrinsic semiconductor we have already discussed. So how we manufacture the intrinsic semiconductor? So if we are moving to next PPT. So this PPT we just move back and we explain here. This is in this PPT you have seen in second figure that we have doped some impurity from outside to make our semiconductor intrinsic in nature, and this element has the pentavalent in nature, that is it has a 5 electron it's in its outermost orbit, and these 5 valence electron, as you see in the figure, pair with the four atom of the silicon semiconductor silicon. So what does it represent? It represents that when the pentavalent impurity adding in the silicon crystal, then these atom share its electron from the 4 atoms of the silicon, so that they share the 8 electrons in the outermost shell and completed the 8 electron to complete the structure, and one electron is free, which is shown by the arrow in the figure. So by adding one atom to a silicon crystal, we have make a one free electron. If we add a 2 atom, we have a 2 free electron, and if we are adding 3 atom, we have a 3 free electron. So this point concludes a very important thing. By adding number of atom, we are increasing number of free electron inside the semiconductor. So by adding more and more atom, we get more and more free electron, means conductivity going to increase. So by adding number of atom, we are controlling the electrical conductivity of the semiconductor. This is the key feature. This is the key point. By adding number of atom, we are in the position to control. If we are adding 4 atoms, we have a 4 free electrons. If we are adding a 10 pentavalent atom from outside in the silicon then we have a 10 electrons. So by this, we are in the position to control the number of free electrons. By this, we are in the position to control the electrical conductivity. That's why we are saying that we are in the position to manipulate, to control, to tune the electrical conductivity of the intrinsic semiconductors by doping. Hope you understand these points very clearly, how we control the electrical conductivity. So here, when we add the donor atom means which have a 5 electrons in its outermost orbit, that is a fifth group elements, and this may available the free electron in the semiconductor. And when we add the trivalent atom in the semiconductor, then we have a basically acceptor impurity, and we have a hole. So that is the p type, and here is the n type. We will discuss more detail regarding p type and n type in further ppts. For here, I think it's time to move in next ppt. Before conclude this ppt, I want to tell some more points. If we add a pentavalent impurity in a semiconductor, then this will make the semiconductor n type, because here electrons are free and electrons are the majority charge carrier. And if I want to make them p type, then I have to add the trivalent impurity. In that case, the impurity atom share 3 electrons from the outermost orbit and one hole is created. So in trivalent impurity, we have a hole availability, and in pentavalent impurity, we have electron availability. So that's why their nomenclature comes from. Hope you understand. Now move further. Now this is an energy band diagram regarding the conduction band and the valence band. Basically, what we have told in next PPT, that outermost shell of the atom, that is basically it contains 4 electrons in case of silicon or germanium. So outermost shell of the atom, basically it's contribute to the valence band. So here we have seen the valence band and conduction band. It is a band diagram of the semiconductor, and there is a band gap between them. Basically, these band gap have a height, and this height is correspond to the energy. And by this height, which we may classify the nomenclature of the semiconductor, conductor, and the insulator. If this height, this band gap is very high, so our material is an insulator. If these bands are overlapped, there is no height between these valence band and conduction band, then this is a conductor, and is this height and this band gap is of the level of 1 electron volt, 7 electron volt, or between or less than the 2 electron volt, then our material comes in the category of the semiconductor. So from here we have a new definition regarding semiconductor. That semiconductor has the band gap between conduction band and the valence band is of the order of 0.3, 0.7 electron volt, 1 electron volt, or even 2 electron volt. But if this gap vanishes and this valence band and conduction band comes together, border to border, then this is the material of conductor nomenclature. And if this gap is very high, it is very difficult to electron jump from valence band to conduction band, then the material said to be insulator. So by this band gap, we have two nomenclature like conductor, insulator, and semiconductor. So by this figure, we just want to explain these things. So this is another very nice figure regarding intrinsic semiconductor. So as you see in intrinsic semiconductor, in pure form, we have a silicon atom, and silicon atom has the 4 valence electron in the outermost orbit. If we want to solidify this in term of material, then these silicon atoms solidify itself in the form of crystal, and this is the picture how they solidify. They just share the 4 electron by nearby atom to complete their outermost cell. So now valence band or the outermost cell has the 8 electron completed. So no electron is free here to move here and there. So this is the pure semiconductor, and this structure is like a insulator. So here we have some important point. The energy band gap for silicon is 1.1 electron volt. That is, it is a height of valence band and the conduction band. For germanium, it is zero point 0.6 electron volt. So basically, pure semiconductor is like an insulator, and when we increase the temperature, some covalent bond which they have made during their crystal formation, some covalent bond broke down when we increase the temperature, and some charge carrier may release. So intrinsic semiconductor makes some conduction if we increase the temperature, but at the absolute zero, it is a perfect insulator. Or even if we increase the temperature, a very slightly charged carrier available. So without doping, the pure semiconductor is acts like a insulator. So this is the crystal structure, and you have seen there is a no charge carrier which is free to move here and there for the conduction of the current. All the electrons you have seen make the covalent bond here and there to form the structure. So this is the figure which tells how the solid silicon crystal looks like. Now move further. So this is the picture regarding the extrinsic semiconductor. First we read some important points, then we explain individually one by one. So extrinsic semiconductor are the intrinsic semiconductor deliberately doped with impurity to improve their conductivity. Doping introduce additional charge carrier like electrons and hole depending upon whether you are choosing the pentavalent or divalent. If you are going to choose pentavalent, then electrons are available to move here and there, and the semiconductor which is available during manufacture is a n type. And if you are take a trivalent impurity for addition in the intrinsic semiconductor, then the holes are available to move here and there, and the which semiconductor which comes out after manufacture is a p type. So n stands for negative and p stands for positive. So here types of extrinsic semiconductor. So n-type semiconductor is one of the type of the extrinsic semiconductor. So as we have discussed, there are some pentavalent impurity or fifth group impurity of the periodic table. Examples are phosphorus and arsenic. These are the element which have the 5 electrons in the outermost orbit. So here donor atoms provides extra electrons. In case of phosphorus, it is electron. Majority charge carriers are electrons and minority charge carriers are hole. Majority charge carriers of electrons means there are electrons which are available for the movement to conduct the electrons, to conduct the current. Basically, in intrinsic semiconductor, in n-type semiconductor, there are equal number of positive and negative charge. But negative charge have the liberty to move, and positive charge are the fixed, but the number are equal. So electrically they are neutral. It doesn't mean that the electron is greater than in number than holes. The number is equal, but in n-type semiconductor, it is the electron which has the liberty to move here and there for the conduction of electron. Holes are fixed and the numbers of charge carrier are equal. Electrically, it is neutral. In case of p-type semiconductor, as we have discussed, if we have doped with the acceptor impurity like boron and aluminum, then these are the element of the third group, and they have the 3 electron in the outermost cell. As you see in the picture, we have boron in the figure, and this boron in the picture share their 3 covalent bonding with the electron, and the one bond we have shown by the circle, it is the leg of the electron, and creation of the holes is here. So one hole is created by adding one atom of boron, and we in this picture we have adding the 3 boron atom in the pure silicon crystal. So we have the 3 holes. So by this we are controlling the electrical conductivity. So that's why we use the term. We may tune the semiconductor electrical conductivity. This is the key feature, key point regarding the electrical property of the semiconductor, regarding the current generation and the next generation also. So in this picture you have seen the p-type semiconductor. The pure silicon crystal semiconductor is doped or substitute by boron from outside to make them electrically active, electrically more conductive. So by this PPT we have clearly seen that how the doping process makes semiconductor more conductive. So hope now we move further. In this picture, as you see, holes are the majority charge carrier. It doesn't mean that that number of holes is greater than number of electrons. No, it is not so. The number of holes is as equal to number of electrons, but electrons are not able to move here and there. They are in the form of the negative charge, negative fixed charge. So it is holes which is responsible for the movement of charge. That's why we are called p-type semiconductor. Positive charge hole are responsible. So keep that in mind. In p-type and n-type, number of holes is equal to number of electron. They are electrically neutral. N-type means negative charge carrier responsible to conduct the current. P-type means positive charge carrier are responsible to conduct the current. So this is another picture regarding the extrinsic semiconductor, which shows very clearly how pure semiconductor share their electron for nearby atoms. Sorry, this is a picture regarding the extrinsic semiconductor, and we show how the pentavalent impurity, that is the n-type semiconductor, make their sharing with the silicon atom. So we have to explain in very detailed manner. So first we have to read some important point, that is conductivity mechanism. Increased number of free charge carrier compared to intrinsic semiconductor. Conductivity depends on the concentration of dopant atom. Key features of doping. Basically, as we know, the enhanced conductivity by order of magnitude, tailored for specific application by varying dopant concentration. So as we have told in early PPT, by the variation of impurity from outside, here is the phosphorus is example. If we control, it is our hand whether we are want to add a 1 atom of phosphorus, 2 atom of phosphorus. So here is an example of 1 atom of phosphorus is adding in the pure silicon crystal, and this phosphorus atom share the 4 valence electron with the other silicon to complete the crystal structure, and it has the 5 valence electron in the outermost shell. So 1 electron is free for the conduction of the electron, which is shown by the arrow, free electron. Then all other electrons make the covalent bond the other neighboring silicon atom to form the crystal. So here, by adding the pentavalent impurity or fifth group elements, we have a 1 electron for the conduction. If we add a 2 phosphorus atom, we have a 2 electron, and if we have a 3 phosphorus atom, we have a 3 electron. So by controlling the addition, or by controlling the magnitude, or by controlling the concentration of the impurity, we may tailor the electrical property of the semiconductor. This is the key feature. This is the beauty of the semiconductor, by which they are so useful in the current generation and for the next generation. So here is some uses of the extrinsic semiconductor, like diode, sensor, and p-type semiconductor used in the p-n junction diode, which we will discuss in the next PPT. So now hope you understand the p-type and n-type semiconductor mechanism. So this is again a Venn diagram picture of p-type semiconductor and n-type semiconductor. As you see, here is a some nomenclature like capital V dot capital B, it is a valence band, and capital C dot capital B is a conduction band. So basically valence band, we have a valence band means a band which is full of electron, and it is consists of the outermost shell of the atom. And conduction band is a some space which is empty, almost empty, and when the electron jump from valence band to conduction band by crossing the band gap, so when the electron move in the conduction band, here is a free space for the movement and current conduct. In case of conductor, this gap is a very small, or even they are overlap. In case of insulator, this gap is very high, and for semiconductor, this gap is of the order of 1.1 electron volt or 2 electron volt, or even 0.3 electron volt. So we have a p-type semiconductor and we have a n-type semiconductor. As we see, when we add the impurity from trivalent atom, then it make a acceptor energy level near valence band, so that electron easily entered in it. And in case of n-type semiconductor, the impurity which we have add from fifth group, or a pentavalent impurity, it creates the energy level near conduction band, which is a full of electrons. That electron easily move from this donor level to a conduction band, so that electron may conduct the current. Now hope you understand the energy band diagram regarding n-type and p-type. So this is again a very nice PPT which show very clearly regarding unpaired electrons, missing holes of silicon atom, and this silicon crystal is doped by the trivalent boron atom. So this is basically a picture of p-type material, and in this PPT first we have to read the important point. So this is a acceptor impurity. As you know, the acceptor impurities are those impurities which are from the third group of the periodic table, and they have the 3 electron in their valence band, and they are responsible to create a hole in the silicon crystal to make them p-type. So in p-type, holes are the majority charge carrier which are responsible to conduct the current. So these things we have discussed in a very detailed manner. So now how it works? When we added a silicon crystal, the acceptor impurity, so they are a hole, and electrons make the covalent bond, and hole act as a positive charge carrier, allowing current to flow when an external voltage applied. So I think we need not to discuss much more. We have already discussed. So this is again a acceptor impurity p-type semiconductor Venn diagram. So now I think we have to move further. So donor impurity of the phosphorus atom and their sharing of the electron with the other silicon atom, and these extra unbound electron. Basically, unbound electron are the free electron, and bound electron are the electron which are in the sharing of the other atom to make the covalent bond. So this is again a very nice picture regarding band diagram of conduction band, valence band of a n-type semiconductor, and we have discussed. Basically, here is some characteristics point of the n-type semiconductor. So as we know, free electrons are the majority charge carrier, holes are the minority charge carrier, and as some applications regarding rectifier and p-n junction diode. So this is a very nice comparison between p-type and n-type semiconductor, and by this PPT you understand better way how they differ between the some specific parameter. First of all, we are going to discuss the doping element. In case of p-type semiconductor, it is third group elements like boron and aluminum. In your competitive examination, this is a very common question asked frequently. Then to make the semiconductor p-type, so from which group elements are available? So these are the third group. In case of n-type, we have a fifth group element. Example are phosphorus and arsenic. Majority charge carrier in case of p-type is holes, and in case of n-type it is electron. Again, I just tell you one important thing. Majority charge carrier means holes are responsible to conduct the current. Holes has the powers to move here and there in case of p-type. In case of n-type, electron are the power to move here and there. Electron are responsible to conduct the current in case of n-type. It doesn't mean that their number is more or less. The number of holes and electron are equal in both case p-type and n-type, and they both are electrically neutral. Minority charge carrier means again there are some electron in a p-type which are move here and there, and there are a very little number of holes in n-type which are move here and there. It doesn't mean that numbers 1, 2, 3, 4. Charge carrier source created by the absence of electron in the valence band. Charge carrier source in case of n-type is the extra electron from donor atom. Electrical polarity, positive conductivity due to holes, negative conductivity due to electron in case of n-type. Energy band diagram. In p-type, we have an acceptor level near the valence band. In n-type, we have a donor level near the conduction band. So hope by this PPT, we conclude the basic theory regarding p-type and n-type semiconductor. Now we move the application. So this is the again a PPT regarding p-type and n-type, some basic applications need not to discuss here. So this is the very important PPT regarding the p-n junction diode. So what is the p-n junction diode? This is the one of the very important application regarding electronic devices formation for the in every circuit, in every instrument we require this p-n junction diode. So first we have to read the point one by one, then we go in the detailed manner. A p-n junction diode is formed when a p-type semiconductor is joined with the n-type semiconductor back to back and creating a boundary at the interface. Basically, join the two semiconductor p-type and n-type back to back as you see in the figure, and the boundary of the junction have the nomenclature by the red line depletion region. What does it mean? It doesn't mean that we have a one piece of semiconductor in our hand which is n type and another piece is a n type and we just join block of n type and p type semiconductor. But it doesn't mean that we have two independent blocks of semiconductor and we are going to touch. No, it is not like that. It is just a figure to understand you in a simpler way. The situation is that we have a pure intrinsic semiconductor by adding some impurity on one side to make them n type, that is a p type pentavalent impurity. On the same crystal, we are adding a trivalent impurity from another side to make them p type, and then automatically the junction is formation between the interface. So it is not like that we have a two blocks of semiconductor p type and n type. It is a single crystal. It is a single crystal originally from intrinsic semiconductor, and we have doping some pentavalent impurity on one side, and on the same crystal we have a dop some trivalent impurity to make them p type, and this p-n junction form. So keep that in mind. It is a not two blocks, it is a single crystal. So it is only just for your simpler way to understand how they works. It is not practically that we are joining the two blocks. It is a single crystal. So we have a n type semiconductor on left hand side, we have a p type semiconductor on a right hand side. So what happened when these two crystals come in the contacts? As we know, in p type semiconductor we have a majority charge carrier holes. In n type semiconductor we have a electrons are the majority charge carrier. So what happens at the junction? Basically, electrons from the n side diffuse into the p side and holes from the p side diffuse into the n side, because these are the opposite charge carrier and they attract their counterparts, and they recombination occurs near the junction. So as you see, there is no battery from the outside. So those charge carrier which are very near, recombination occurs and the junction near junction is free from the mobile charge. What does it mean? It means that there is no free charge available near in the yellow part of the PN junction diode. We will discuss it in next PPT in a very detailed manner. For here, as you just understand, in the yellow part, there is a no free electron, and the region which is free from mobile charge is called depletion region. So depletion region is the region of the PN junction diode where we have a fixed charge. We don't have any mobile charge. So keep that in mind. Depletion is the region inside the PN junction diode where we don't have any mobile charge. We have a charge, but these charge are fixed. They don't have power to move here and there. Okay, so now recombination forms and the formation of the depletion layer here. So in this PPT, we have a PN junction diode, the formation of the depletion region. Now move further. So this is again a Venn diagram. We are not here to discuss this PPT. Now move further. We have already discussed the Venn diagram. So this is the behavior of PN junction diode under the forward bias. What does this mean? It means that when we applied the positive terminal of the battery to the p type and negative terminal to the n type, then this condition is known as forward biasing. In forward biasing, we are going to connect the positive terminal of the battery of the p type and negative terminal of the battery to the n type. So basically, in forward biasing, we are going to increase the variable battery source, then the voltage increases, and when this voltage reach to the certain level, for the case of silicon this voltage is the zero point 0.7, and for the germanium it is the 0.3, then the electron conduct and the current vary with the voltage. So we will discuss these voltage known as the knee voltage. So what is the knee voltage? Knee voltage is the minimum voltage from where the current is ready to start to move with the voltage with the linear relationship. It means that if we increase the voltage, instantaneously we get the current. So current is linearly vary with the voltage. Before 0.7 volt, in case of silicon, current is not linear with the voltage. Before zero point 0.3 volt in case of germanium, current is not linearly vary with the voltage. So these are the two special points regarding your competitive examination, that knee voltage is the voltage from where current moves like a linear relationship with the voltage. Yeah, or in other word, current is ready to move. So before zero point 0.7 volt in case of silicon, there is no current, and before zero point 0.3 volt in case of germanium, we have a no current in our deflection instruments. So knee voltage, I think you understand. The knee voltage is the minimum forward voltage required for the diode to conduct the current significantly. After the knee voltage is reached, the current increases rapidly with further increase in the forward voltage as the depletion region becomes vanishes negligible. In other words, depletion region means the resistance. Depletion region means the obstacle. So when you uh, make a p-n junction diode, then we have a depletion region. Basically, depletion region consists of the fixed charges, positive charge on n side, negative charge on p side, and they make a dipole, and this dipole have the electric field, and very soon after the formation of the junction, this electric field is so strong which may stop the further movement of the charge carrier, and this is the magnitude of the electric field which is correspond to the voltage zero point 0.7 and zero point 0.3 for germanium and silicon. Now move further. So this we have discussed some other points we have already discussed in case of a diode. Case of germanium, we have a no current in our deflection instruments. So knee voltage, I think you understand. The knee voltage is the minimum forward voltage required for the diode to conduct the current significantly. After the knee voltage is reached, the current increases rapidly with further increase in the forward voltage as the depletion region becomes vanishes negligible. In other words, depletion region means the resistance. Depletion region means the obstacle. So when you make a p-n junction diode, then we have a depletion region. Basically, depletion region consists of the fixed charges, positive charge on n side, negative charge on p side, and they make a dipole, and this dipole have the electric field, and very soon after the formation of the junction, this electric field is so strong which may stop the further movement of the charge carrier, and this is the magnitude of the electric field which is correspond to the voltage zero point 0.7 and zero point 0.3 for germanium and silicon. Now move further. So this we have discussed some other points we have already discussed in case of a diode. So this is a picture of the IV characteristics of the p-n junction diode. But from this picture, if we have to discuss some more points, this is the formation. Let's move further. So here is a picture regarding the p-n junction diode in reverse bias. We have discussed the forward bias. Now this is the reverse bias. As you see in the reverse bias, we have connect the negative terminal of the battery to the p side and the positive terminal of the battery to the n side. What does it make some changes? Yes, it makes some changes. It increase the width of the depletion region. Keep that in mind. Forward bias decrease the width of the depletion region. Reverse bias increase the width of the depletion region. In other words, reverse bias increase the resistance near the junction. Forward bias decrease the resistance near the junction. Or here, the depletion width, the region which is free from mobile charge, the region which consists the dipole, depletion region which consists the fixed charge. So keep that in mind. Reverse biasing increase the depletion width. So in reverse biasing, we have a negative terminal connection with the positive side and positive terminal connection with the p type. So hope you understand. So first I read the reverse bias definition. When the positive terminal of a power source in the figure is connected to the N side cathode and the negative terminal to the p side anode of a p-n junction diode, it called the reverse bias. Effect on depletion region. The external voltage increase the width of the depletion region. So basically, this is the basic physics how reverse biasing works. So if we want to conduct less current or if we want to block the current in a circuit, we are we have to use PN junction diode under reverse bias. Reverse bias has the large resistance due to the depletion with increase. So in forward bias, we have a connection like that. The width of the depletion region decreases continuously as we increase the outside voltage source, and soon after reaching the value zero point 0.7 electron volt for the silicon and zero point 0.3 electron volt for the germanium, the situation is where the electron enters in the depletion region, and so that as soon as the mobile charge enter in the depletion region, the depletion region vanishes and the continuous flow of electron circulates in the circuit and the circuit completed in the forward bias. So current conducts and the situation soon reach which is called the knee voltage. So now move further. So this is the curve which we have to explain here. So as you see in this curve, we have a on x-axis we have a current, and sorry, on x-axis we have a voltage, on y-axis we have a current. So as we increase the current, we have a show a blue line which move upside forward biasing, and the dotted red line which breaks the blue line, some position is disturbed during the plotting this curve. Exactly, this red line shows the position where the blue line ready to move upward, and this is the position the on the x-axis where the blue line just leave the black line bottom line the x-axis. The point where the blue line just leaves the black line to move upside is the point of the knee voltage. So knee voltage is the voltage on forward biasing where current ready to start with the voltage. As we see after knee voltage, the current shows the linear relationship with the voltage. So in case of reverse biasing, as we in the reverse biasing, as we see, there is a no current flow up to a very large negative voltage, and after that a very small amount of current flows regarding the minority charge carrier. So basically this is the IV characteristics curve of the diode, and we see in forward bias the current is rapidly grow with the voltage, and in reverse bias the current is almost zero as we increase the reverse bias. So by this figure we shows that the diode conducts the current in forward bias and doesn't conduct any current in the reverse bias. So this is a very useful application in the rectifier. So for rectifier applications, the PN junction diode is an ideal circuit. So when we want some signals, we just make it in the forward bias position of the diode, then easily pass the signal. And if we make the reverse position of the diode, then it blocks the signal. So how does it? So that's why the PN junction diode is work as the rectifier only because of the conduction of current in forward bias and block the current in the reverse bias. So in forward bias, it offers a very low resistance. In reverse bias, it offers a very high resistance. That's why we use PN junction diode as a rectifier. So move further. So this PPT we have discussed. So this is the behavior of PN junction diode under reverse bias. So if the reverse voltage increase beyond a certain threshold, which we have shown the blue line on the left hand side, the diode may undergoes reverse breakdown, and this may create some charge carrier and some small amount of current you observe in the deflection instruments. This is the reverse saturation current. A very small constant current flows under the reverse bias, which is of the order of microampere. So in some competition point of view, So reverse saturation current is of the order of microampere, and the forward current is of the order of the milliampere. Keep that in mind. Basically, no significant current flow during reverse bias during large resistance offered by the depletion region. So this is a some application here. Reverse bias is used as a rectifier purpose in photodiodes, and Zener diode is one of the most application of the reverse bias. So this is a PN junction diode characteristics curves important points. I have to read one by one. Some basic overview of the IV characteristics curve of the PN junction diode. The current voltage characteristics curve of PN junction diode illustrates the relationships between the applied voltage and the resulting current. The curve provides the critical insights into how the diode behaves under forward bias, the right part of the curve, and the reverse bias, which we have shown on the left hand side. Some key reasons in the IV curve: the forward bias region, the threshold voltage. Initially, the current is negligible. I just want to show this is the initial point which we have the right hand side on the x-axis before the blue line, where the blue line just leaves the black line on the x-axis. You have seen that the current is zero. So this is the part. So this is the point which we have discussed here. So the curve start flattened and then rises sharply with the threshold voltage. So sorry, this is the forward bias region. So initially the current is negligible, which I just shown you, until the forward applied voltage reaches the threshold value, that is the knee voltage. So knee voltage is the voltage in the curve where current just leaves the x-axis. This is 0.74 case of silicon and 0.3 in case of germanium. So just exponentially rise after the threshold voltage reaches, and low resistance in case of forward bias. And this is the reverse region points. We have discussed already that reverse region we have a depletion region wider, large resistance, very small current. So now move further. So the last session comes out the question and answer session. So this is a very important session regarding your competition examination. First of all, we have a what is a PN junction. I hope now after this lecture, you all of you have a very good knowledge regarding PN junction diode, regarding basics physics, regarding semiconductor. So a junction formed by joining p-type and n-type. This is the correct answer. The next one is that what is the depletion region in PN junction diode? So the region with no free charge carrier. So we have the other options. So read carefully every option before to attempt the question. Now, what is the main purpose of a PN junction diode junction in a circuit? As you know, it has a function like that. It blocks the signal in reverse bias, and it is very easy to flow the signal in the forward bias. So it acts as a rectifier. So if we use it in a reverse bias, it is a signal blocker. What is the typical knee voltage for a silicon? It is 0.7 and 0.3 in case of a germanium. In forward bias, the current in a p-n junction diode is very large after knee voltage, and in reverse bias, it is a very small. In reverse bias, the current in a p-n junction diode is mainly due to, you know very well, in reverse bias, the current is only due to a minority charge carrier. In forward bias, the current mainly due to a majority charge carrier. So this is all about this lecture. So wish you very best of luck, and I hope this lecture gives you very detailed view regarding the physics behind the PN junction diode and semiconductor. Wish you all very best. Thank you.